Just to present briefly your biography, Thomas, you are you are managing director of Transsolar, which is a distinguished world-class climate engineering practice, which has received international attention over the last 3 decades and is working on all scales from single buildings to urban neighborhoods. You have always advocated an understanding of energy efficiency that goes beyond technology. And you are also professor of building technology and climate responsive design at the Technical University of Munich. And you advocate a very comprehensive understanding of user comfort balanced with innovative and sustainable design strategies. You will present us today your vision on climate responsive building design. It's an honor for us to have you. I wanted to mention that we hope that next year, if COVID crisis has diminished or disappeared, that the next year class of this executive master, we have the chance and the opportunity to meet you again in München, because it was an unbelievable week, and I wish all my colleagues from the next executive masterclass to have this chance to have this study trip in Europe. So you will present us today climate responsive building design. So I don't want to mention too many things about what you will say, but you will talk about high tech and low tech. You will talk about robustness. You will tell us about the energy targets and also the user comfort targets. Can they be achieved or not? The impact of technology, the passive and user control systems, many very interesting things. So it's, I think, your turn now to present ourselves, your presentation. And Thomas, thank you again. And I give you the floor for the presentation.
Yeah, Frederic, thank you very much for this very kind introduction, and also glad you enjoyed the time in Munich. So 2 years ago you visited in Munich. Now I have the possibility to visit your event, even though it's just digital. I would much more preferred and enjoyed being in Paris today, but hopefully soon we can do this again. Just one question. You see my presentation only, or?
Yeah.
Yes,
see absolutely. We can see it.
Yes.
Yeah, okay. So I will talk a little bit about high-tech, low-tech, robust. There's a bit of a debate over the last decades, I have to say, whether high-tech or low-tech, how we can approach building design and how can we, let's say, reach our goals of decarbonizing the building stock. And can we reach this by technology, or do we need to have other solutions? So that's the aim. We have to become carbon neutral. And we see a lot of these kind of things where gadgets are applied on a building, and the building is already stupid to begin with. And so we are totally convinced that we have to become much smarter, that technology has to serve people and has to be integral to an architectural approach. We have to hybridize things. And what I mean with this, I'm going to show you in a second. But it's not only about decarbonization. I mean, we design buildings and we design our built environment for people. And so therefore, we need to have a deep and thorough understanding of what creates environmental quality, what creates comfort, and what creates healthy environments. And I always love to show this picture, which we took from a magazine where they said, "Welcome to the breathtaking Tokyo water park." And then the next line was, where you can wash away the pressure and stress of the overcrowded city. We really like this picture. You might wonder why. In terms of sustainability, let's say it's probably negligible how much energy they use in this water park, because the energy consumption per person is negligible, because so many people use it. They love this place, they go there, they use it. On the other hand, we can design a zero energy building. If people hate it and they don't use it, it's still a waste of resource, the resource land, other resources, materials, etc. So we can't disconnect sustainability from environmental quality, from architectural quality. We need to create spaces people enjoy and people use, and so that people love the place, people love the building, so that the building will also last. I mean, most likely there's a lot of buildings do not last long enough, which is also a problem in terms of sustainability. If buildings are teared down after 20 years of lifetime or 30 years, this happens not to buildings people love, people enjoy. Like take the Eiffel Tower in Paris, nobody would tear it down. There's certainly an extreme example, but you can see many more examples in the city of Paris. So let me show you a project I did, or we at Transolar supported already in the year of 2005 or so. We worked on this building. It got completed in 2010. It's a high-rise building in Canada, in Winnipeg, where we worked with KPMG architects and many others. And it's the main headquarters for Manitoba Hydro, the utility company in Winnipeg. And they aim to have the most energy efficient high-rise building in North America. So this was, let's say, one of the aims of this building, among others. The most important one was healthy and inspiring workplace environment, but also then contributing to downtown Winnipeg, trying to revitalize the inner city, signature architecture, but also at least LEED Gold, they stated when the client described the goals. So we started to analyze the climate like we do it all the time, and we figured out that Winnipeg is actually very cold, with temperatures going down to minus 35 degrees, and it can become very warm and humid, particularly in summer. More muggy than what we are used to in Central Europe. But then whenever we talk to people, everybody said, yeah, it's getting cold here, freezing cold, but whenever it's really cold, it's always sunny. So we started to dig deeper into radiation data, and we found that there is no single location we have in Germany which has as much solar radiation as the city of Winnipeg. It has almost as much solar radiation annually as the city of Rome. And so we said, and a lot of it in wintertime. Then we looked on a vertical south facade, how much solar radiation we have on a vertical south facade, and on a vertical facade, due to the low sun angles in winter, you get more exposure on a vertical facade in winter. And we recognize that we have more solar exposure on a vertical south facade in winter than we have in summer. So over a lengthy design process, we ended up with a scheme where we have an 18-story tower on a 3-story podium. And the 18-story tower, where 2,000 people are supposed to work, we divided into what we call 6-story neighborhoods. And each neighborhood has a south-facing winter garden. And so what we do in winter, we get fresh air entering it in the south-facing winter garden, and we condition the air before it enters to a temperature of 10 degrees. And then we have a water curtain that provides some level of humidification. And then the sun that is hitting the south facade further heats up the air before it gets distributed by a raised floor planum into the depth of the floor plate. There we take the air on the north side, putting it into a chimney where we draw it down in the basement, where we have a heat recovery unit, and through a hydronic loop, we bring the heat back to the supply air units, which are integrated in the winter gardens. And then we have piping embedded in the floor slab which provides some radiant heating in wintertime, cooling in summertime. And then we have almost 300 boreholes for a geothermal heat exchanger under the building, connected to a heat pump, and the heat pump lifts this geothermal heat onto a useful temperature to make it useful for the radiant heating and for air heating in the building. And then in summertime, as soon as we do not need heat recovery, we exhaust naturally by this solar chimney. We open up the south facade so that we get basically outdoor conditions in this south-facing area. We run cold water from the geothermal system through the slab, and we have this natural exhaust. So this is how the building works. Here you see the south-facing winter garden, which is basically the mechanical room of the building. So all the air supply units are integrated in this bench you see on the right side of the image. Behind the panels you see on the left side of the image, there are the units which take the air from the winter garden and distribute it into the office space by a raised floor plenum. This is the water feature, which provides some humidification and then some shading devices so that people are not exposed to the sun in summertime when we don't need the passive solar heat gains. And here, this is where we can open for natural ventilation so that in summer, the space doesn't overheat. To the east and to the west, we do have a double facade. And it has a couple of reasons, but the main reason is that we do get the shading device, a retractable Venetian blind, outside the conditioned environment into this facade cavity. By product, we have operable windows, which is very unusual in this extreme cold climate. We control the outer openings in the outer facade so that we can dissipate the heat that piles up in this facade cavity in summertime to dissipate it to the outside. But however, what was very important is that we get the shading device out of this conditioned environment so that the radiant cooling, the limited capacity of a radiant cooling is sufficient to cool the space, and the supply air, the fresh air is coming from below, and then people can open the window whenever they want. So what does this all mean in terms of energy? MNECB was the Canadian energy code when we designed the building. It requested that we stay below 260 kilowatt hours per square meter and year. And our modeling, our computer modeling has shown a number below 90 kilowatt hours per square meter and year. Then we started to operate the building, and first of all, the good news, in terms of service calls for too hot and too cold, in the third year of operation, compared to the other buildings Manitoba Hydro operate, which are fully air conditioned, we have only half as many calls, half as many complaints for too hot and too cold, which is quite a surprise, given the fact that the radiant system, we have no real control over the indoor environment. Since it's embedded in a 30 centimeter thick concrete slab, it reacts so slowly that if people complain that the space is too hot in summer, it takes 24 hours to reduce the temperature by about 1 degree. So there is no control over the space. We condition the space at, let's say, in a hot period to an indoor temperature at the end of the day of 26 degrees, unlike 24 of what they are used to in their other buildings. And still, even though there is no control, no level of control in summer nor in winter, we have only half as many complaints, which is quite a surprise. And I think we can have long debates why this is the case. And then they looked at sick days, and they found that in this building, we have 1.25 less sick days compared to their other facilities. X is a secret of Manitoba Hydro. They never told us what how many sick days they usually have, but in this building they have 1.25 less sick days. This is both a really good result, let's say. Particularly the Canadians or North Americans, they always have this rule of thumb. They say if we pay $1 per square foot for energy, we pay over, let's say, if we rent a building, we pay $10 a square foot for the rent. But we pay $100 a square foot for the staff, for the people working in this building. So if we translate this number into, related to the 2,000 people working in this building into dollars, then we end up with a number which is somewhere between $2 and $3 million, whereas the total energy savings only sum up to less than $1 million. And not talking about that people feel more comfortable because every workplace is exposed to daylight, and coming back to these question of calls, obviously people also have a better thermal comfort. Not talking about to their increased productivity while they are at work, only the hard fact of sick days. Now the bad news, so we monitored the building over a period of 2 years and recognized that it almost took us 2 years before we reached the predicted numbers. So that was a shock. So we thought it's not a rocket science, this building. I mean, it's pretty straightforward. It's not super complex. It's not super high tech. Why did it take 2 years? And this is what we call performance gap. So what you see here is the energy consumption the first month, September 2010, when we had a full year of operation. And then October 2010, November 2010, and so on, always looking at the previous year. We had some hydronic issues, which got fixed here, what you see, but and it was not a single major problem. There was this one hydronic problem, but it's a million of things, not a million of things, but a couple of hundred of small items. A sensor, which is not sensing a correct temperature, a routine, a control routine, which is a little weird, these kind of things, and you have to find them. You have to find them and fix them before you reach the number we have predicted or projected in design. So this is then again a picture showing this north-facing winter garden chimney, solar chimney, which operates the natural ventilation when we don't need heat recovery outside the winter season. So, I mean, coming back quickly, so we developed a system where we showed, not only with this, with many other buildings, that with this kind of adaptive facade systems, buffer zones, etc., we can have all glass buildings, even in extreme climate, reaching very good comfort conditions, reaching very low energy numbers. So that was the result. So it's still one of the most energy efficient high-rise buildings, probably the most energy efficient high-rise building which got ever built in North America, in one of the most extreme climates of North America. It's the coldest capital city worldwide, Winnipeg, the city of Winnipeg. It's the capital of the province, Manitoba. But what we see is nobody ever tried to copy this approach in North America, except for ourselves. And if we look at all the glass buildings that get built worldwide, here you see a picture of Dubai. We see totally stupid buildings, all glass, no adaptivity, just using a lot of coating to deal with the heat and the solar energy that comes with the facade. And the whole stupidity becomes obvious when we recognize that a lot of people in the Middle East complain about something we call SAD. It's a disease which is caused by the lack of sun exposure in the Middle East. It's because there's so much coating on this glass that you don't even get enough sun to, let's say, to create vitamin D and other hormones the body needs to stay healthy. So nobody tries to copy it. So, and it's a very unstable or kind of very, let's say, a system, a model, which lacks robustness. It required 2 years of fine-tuning to get it to operate appropriately. So I don't want to say it's not a successful building, and it's an extremely successful building, but we have to question whether the model is a successful model. And so we have to conclude, and that's my first hypothesis for today, that glass architecture failed as a model in terms of robustness and sustainability. So we started at the university, we started to dig deeper into this question of performance gap. So we wondered, is it just our problem, or do we see this more often? We found this study done by the Royal Institute of British Architects, RIBA, called Better Spaces for Learning. They figured out, they looked at 60,000 school buildings all over Europe. They figured out that 95% did not perform as intended. So we recognized that this question of performance gap is not only a problem of Manitoba Hydro and this kind of adaptive building approach, it seems to be a general problem, 95%. So it's not the exception, it's the norm. And then this project was, this research was done in Germany by the Technical University of Braunschweig, called EFA. They figured out that buildings in average, it was about office buildings, use 70% more energy than predicted, 70%. So someone recently said the building sector will be the next sector which has the Volkswagen moment. So if you look at those numbers, as soon as those numbers get into the public, get discussed in the public, our sector has, the real estate sector has the Volkswagen moment. And then also interesting, naturally ventilated buildings have a 30% lower primary energy consumption compared to buildings with mechanical ventilation, even though all codes tell us the opposite, that mechanically ventilated buildings are more energy efficient. Main problems is what they figured out are mainly control systems. So at the Technical University, we did some studies. We wrote 2 books. Sorry, they are both in German, but I want to show you the first one, just a few slides where we compared 12 schools. 12 schools, those are the 12 schools we looked at from different periods, starting with a school building from Theodor Fischer, an architect from Munich, which got built in 1898, and then built a building in Amsterdam from the modernism from the 30s, a couple of buildings from the 50s, 60s, 70s, which got renovated already, and then 2 buildings which were designed as a passive house school, just let's say recently, about 10 years old, and then a brand new building designed by my colleague, who was co-author for this book on schools, Florian Nagler, and it's a timber building. So very sustainable. It's all timber, massive timber as a material, as a main material for the construction of this school. So those were the different classrooms, and it's quite interesting because looking at these pictures, we also see the different measures that have been done for acoustic to improve acoustical performance. And then we did measurements in our buildings, and I don't want to go into the details, but we looked at temperature, we looked at humidity, we looked at acoustical performance, reverberation time, and we looked at air quality in particular. And what we figured out, and I can shortcut this is looking at CO2 during occupation. What we figured out is that the Theodor Fischer building, this is the mechanical rooms, where the Theodor Fischer building from 1898 has a boiler room of something like 30 square meters. The brand new buildings down here, you have a gym for the air handling units under the building. Like you have a huge space under the building to deal with all the mechanical system. So again, this is the classroom of the Theodor Fischer building. And so what we figured out among all school buildings with natural ventilation. The Theodor Fischer building from 1898, the 120-year-old building, had the best air quality. Among all buildings without mechanical cooling, in this building we had the best thermal comfort. We had perfect acoustical performance, even though there is no absorption at the ceiling. And we have very even and very good daylight conditions. And why is that the case? I mean, it's very simple. The space has 80 square meters per classroom instead of 60. And it has a 4-meter floor to ceiling height instead of 3 meter. So we have almost twice as much air volume per user, per kid in this classroom. Due to the height, we get these tall windows, which gives us daylight deep into the space. Because of the tall windows, we have a lower fenestration ratio in combination with this kind of 70 centimeter thick brick walls. We have so much thermal mass that the space doesn't overheat. Due to the height of these windows, we have these curtains for sun and daylight control. And those curtains are so tall that we get sufficient acoustical absorption. So in terms of air quality, in terms of thermal comfort in summer, in terms of acoustical comfort, in terms of daylight, this building is the best among all with no mechanical support, or other buildings need mechanical support, which lead to those kind of mechanical rooms compared to the boiler room in this 120-year-old building. So we have to ask ourselves, do we want to build space above ground or below ground? What have we learned in 120 years of architectural progress? This building has had no major renovation in 120 years. Think of all the glass towers we build today, even we build. It's inconceivable that there will be no major renovation in 120 years. So I'm going to jump over this, but we use this also in our research we call Build Simple, or Einfach bauen in German. Research we do at the university with Florian Nagler, an architect at the university, Prof. Kolek at the university, but also running an architecture office in Munich. And we said we have to simplify mechanical systems, but we also have to simplify construction. And we said we have to go back to do monolithic structures, monolithic walls. And we looked at 3 different materials, insulating concrete, timber, and brick. And then we said, like, if we do tall spaces, tall windows, the windows can become narrow. We get good daylight. We don't need the shading device. Shading device can go. If we think about installation and how we install, we don't need to have this kind of floating slab, floating screed. It can go. The wall need to insulate, no exterior insulation. So from this detail, we got to this detail. The same for a timber building, still the timber having the most complicated wall assembly, and then to the brick building. And so let's get rid of everything we don't need. Can we fix it by design and not using all these layers? Same with mechanical systems. Then we were going into a parametric study and said, what kind of space configuration is providing us this quality of the Theodor Fischer building, basically. We ended up with almost 4,000 options we modeled and added some robust optimization, that's how we call it. And so looking also at uncertainties. I mean, that's the problem of our time, uncertainties, imperfection we have on a construction site. So can we design buildings that react so robust so that if the user keeps the window open, the system does not fall apart? The numbers are not getting absurd in terms of energy consumption or in terms of indoor qualities. So we looked at what could be uncertain boundary conditions I said it could be the user, how the user opens or closes the window, but it could also be a shading device which fails. It could be internal heat loads if the user runs a server for Bitcoins, for instance. But it could also be climate. I mean, climate is going to change. Those are our uncertain boundary conditions. And we said which type of system, which configuration, let's say going back to all of those, react most robust onto this kind of uncertainties. And so then we did a life cycle analysis. Again, many chairs are involved in this research. And we figured out that, let's say, this kind of robust, not necessarily energy optimized, but robust optimized systems over even the brick building, if we look at material over and operational energy, like embodied carbon as well as operational energy over a period of 100 years, we are better compared to a passive house. And so what you see here is the uncertainties due to the user, how the user operates the windows. But we end up, no matter which type of user we look at, we end up being after 100 years better than a passive house. So then there was a developer nearby Munich in Bad Aibling who was interested in our research. As he said, come on guys, I'm gonna build you 3 of these buildings. So you see here the timber building in the middle, the brick building to the right, and the concrete building to the left. And the buildings are now rented. We started to do monitoring to see how people use the building, but also how the building is getting conditioned. And we not only said monolithic wall systems, we also said just, let's say, pure materials with no mixture, no composites. So even in the concrete building here, we said no composite. So if we say no composite, means no steel in this concrete. And if we don't put steel in concrete, we can't have a beam. So if you can't have a beam, that's why you suddenly see this kind of arch type windows. So funny that we get back to this kind of, let's say, more historical forms in a kind of a new interpretation. The same with the brick. So no concrete beam. So the masonry, the bricklayer came and used the masonry to create this kind of arch, so that we have no mix, no composites of materials. So if we look at the embodied, just for 1 square meter of wall, if we look into the embodied carbon, just as an example, and then you see here the worst embodied carbon you use for a double facade, a floor to ceiling all glass double facade. So glass actually requires a lot of energy in, let's say, in this generation of glass. If we look at concrete and styrofoam, it's already less. Brick, sorry for using German words here, but brick is half as much of a glass facade. But then if we use something like clay, rammed earth, in combination with, let's say, a natural insulation, it can even become negative. So the point I want to make here is that we can't reduce this question of embodied carbon only to kilogram material used. It's a question of what kind of material used. And maybe we can indeed come back to thick walls. And so that's the second hypothesis, that massive buildings are per se more robust. However, this doesn't necessarily lead to more embodied carbon. And I want to finish with this building, which is the headquarters for Alnatura. Alnatura is a supermarket chain in Germany for organic food. And it's designed by Haas-Kuck-Zemrich architects from Germany. And we used rammed earth as a raw material to create this kind of low-tech passive design. And here then Martin Rauch Lehmton Erde, a company from Austria. They came in with their machinery, and they have, let's say, industrialized the manufacturing of rammed earth walls. So they got prefabricated with here a layer of insulation. You see a horizontal section basically of this wall assembly. So this is foam glass as a mineral material with rammed earth on the outside and rammed earth on the inside. And rammed earth has low carbon, doesn't need a lot of energy for production. It's available everywhere. France has a long tradition, I learned, in rammed earth constructions. There are buildings that are hundreds of years old. People don't even know it's built out of rammed earth. Roger Bolzhauser, an architect from Switzerland, he wrote a book on rammed earth buildings, and he looked for examples all over Europe, and most examples he found in France, which is quite interesting. And so it was all prefabricated. We embedded piping for heating and cooling. And one of the reasons we used rammed earth was, let's say, to lower the energy consumption for building the building. So Martin Rauch, he created this warehouse, or he rented a warehouse nearby the construction site where he built this wall assembly early on. But also rammed earth is still the best material to control humidity in a space. So it's also for humidity control, for climate control, a really good material. And then he brought, with a cherry picker, he brought these wall assemblies on site. And here you see a couple of images, how the building now looks like with these rammed earth wall assemblies. We did measurements where we proved, I don't want to go and show it to you and explain it in detail, but we have shown that we can control humidity with this material in this building and create comfortable environments. And here you see some final images of this wall assembly and the atria in the center of the building, where this north-facing skylight on the south roof, we have a big PV system where this north skylight provides good daylight conditions into the building. And final image, this is how it looks like. Thank you very much.